everyone could get on Slack. Try work.
I'm slow.
No, you were the fastest, I think. The pioneers you try. Okay. Then let's just get into it. So today I thought to just talk about this language or ideas, whatnot, that people proposed to force other people to think like transformers. So there is this paper called Thinking Like Transformers, and this is one of my favorites. And this is a paper that introduces this language. So R stands for restricted. A stands for access. S stands for sequence. P stands for processing. And there is a variation of this that we're going to talk about. So that's a dash and an L. A dash is a dash, and L is learnable. But that's kind of, we'll talk about it. So that comes from a different paper that was a follow-up to the first paper. And the authors of the second paper found that these original ideas were a little bit too broad, and they restricted it a little bit further. So it's like the restricted access sequence processing thing. So transformers. We have a bunch of building blocks in transformers, namely two MLPs. They do processing token by token. So this is like this component-wise application of a function. As was briefly mentioned, MLPs are powerful, especially if you had multi-layer MLPs. Okay, in transformers, you have one hidden layer that's not too powerful, but you have many of these potentially sequenced after each other, so that's effectively multi-layer. And because of that, you can think about that in the token space, you can represent almost every function. So one of the building blocks of this language, so this language, you should imagine that it is kind of tries to abstract away even further, maybe, the details of how transformers compute. What I presented before was already a little bit abstracted. We had workspace and whatnot. So these guys are like, let's put this on computer. Actually, my version of presentation was very much geared towards this kind of thinking. So kind of reverse engineer what was the essence of this thing, and it just formalized that. That was what you have seen before. So one of the building blocks of this language is going to be a function. So all of these functions are taking sequences of some length, and they should be returning sequences of the same length, like the individual blocks in the transformer. So one of the blocks in the transformer is the MLP block. So that you can model as applying some function at every position, and you apply the same function. So the input is a sequence, and okay, so one implementation that we're gonna play with is a NumPy-based implementation. So in that implementation, the sequences are sequences of integers. And this is good for conceptual playing around with like what you can do. So the tokens are themselves integers. So the L learnable as a learnable version of the language, or like this set of ideas, restricts the integers to int 8, like 8 bits. So the elements of these sequences are just integers that can be represented with 8 bits. So this is going to be like minus 127, whatever you can represent with 8 bits, something like that, 128, depending on the convention you're using. So you have a sequence which is an array of int 8, and it's going to be a NumPy array. And one of the things that you can do is called sequence map. It is what you think it should be. It's this function that takes a sequence and it takes a function that maps int 8s to int 8s. Any such function is eligible as a second argument and applies component-wise the function f to each element of the sequence, composes the result and returns that. If you want, you can write it this inline Python thing, which is not how it is written, but like, why not? You take the ith element of the sequence, you apply f, and then you are doing this for all positions in the range up to the length of the sequence. So notice that this function is like of the good type that doesn't change as you're changing the length of the sequence. So there is nothing good about the length of the sequence. Any sequence length can be processed. And so that was what was important with the transformers, with this uniform kind of processing. So that's going to be a key element of everything that we do. So another function that, or building block that we have, of course, is that models what attention layers can do. So what attention layers can do is that they take some sequence, a key sequence, they take a query sequence as well, that's a second sequence. They also take a third sequence, the value sequence. They also take a predicate. The predicate is used for every pair of the key and the query for every position ij, and the predicate should return true or false. And this creates this matrix. That is n by n, if n was the length of both sequences. All sequences have the same length here. That's when things are well formed. Yes?
So the predicate can be any logical operator or just comparison?
Any logical operator. Yeah. Again, this is like, it's like, maybe transformers can't really do that, but after appropriately pre-processing the keys and the queries, the feeling is that, yeah, maybe you should be able to, because the key query processors are themselves little neural networks, and so even if you have just some primitive operation like in a product, you can pre-process things in such a way that any predicate operation will be possible. All right, so we have this predicate matrix that you filled, which is the attention matrix, and then for the output, basically wherever you have a true position, you take the corresponding values, and there is an aggregation function that you run on the top, and the aggregation function can be 3 types. So this is in this specific language, and it's kind of weird. So one of them is mean, and it's not the sum. Why it's not the sum? I don't know. And the other is the max, and the third is the mean. So this is the aggregation functions. So a key sequence comes in, a query sequence comes in, the value sequence comes in, there's a predicate that comes in, and then there is a type of aggregation operation that comes in, which is one of mean, max or min. There is this function which is going to be implemented something like you create a ij, which is the predicate applied to so I have the query comes first, I think, and then the key comes second. So that's just the convention that we are using. And then there is this selection, which collects all the values for, so this happens for all I and j, and then for all I positions, you collect all the values, let's call it, I don't know, capital VI. So here, you put in Vj for j in n if Aij is true. Okay, so this is not proper syntax, but you got a sense of it, right? So you're picking out from V the values where in the attention you wanted to attend to those positions. So the query was formed for this position I. So position I is seeking information. The keys are formed independently. Yeah.
Sorry, what did that say? Aij is equal to?
True.
Oh, okay.
Yeah. Yeah. So the predicate calculated either true or false. Okay? And then you're collecting all these values. Previously when I was writing this, with a formula, it was just a sum over all these values. And the attention was just 0 or 1. It's variation, right? True or false. Pretty much the same thing. And then the aggregation is going to be applied on the so collected values. So in the output, you put position I, the result of aggregation applied to this capital VI. So you do this for all I again. And then you return the output. Yeah.
So is the attention score always either 0 or 1, or can it be like a number in between 0 and 1?
So here, it's going to be true or false. This is abstracting away this, real numbers, no real numbers. Yeah.
Isn't the whole mean thing supposed to represent like a softmax? So you like average over all the things?
Yeah, it is supposed to, but like it's just so weird because we said that we're gonna have everything is an intake. And what the heck are we doing with dividing by n? The length of the sequence. That's so weird. And then I don't even know like whether they are going to round it or not, or like what the heck is going on. So the mean is like really weird for me in terms of this abstraction. But yes, I understand. It's because somehow the mean rep is the closest to the softmax attention that people actually use in practice.
Isn't it also because you don't want the size of it to depend on how many things you send it to? Like what if you
Somehow, yeah, like you don't want the values to grow. Somehow. I mean, you could have some other aggregation that doesn't let that go, but yeah, like the sum would grow with the size. And then you would need to be careful with not causing overflows. But which one is better? I don't know. Because here you start to divide by things and then you create some trouble with that, I think. Okay. So there are these, basically, there's this function, sequence map, and the key query value. And you can use any Python function manipulating int dates on sequences. And there is one more thing, because you want to, sometimes you produce in a transformer 2 sequences, and then you want to join them. Oh, I think that's called seqmap. Like this, like the names are hidable. This is called token map. And then when you have 2 pairs of inputs, and you're combining them position by position, so that's just like maybe you're adding them up or something like that. That's called sequence map. So that's the third building block that you kind of need.
In Python that would be zip.
Yeah, that's actually implemented with zip, blah, 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 right? Like you're zipping together and then you're applying a predicate. So there is sequence 1, sequence 2, and then, no, not predicate, but some function that's applied. But since I'm not that advanced, I just write sequence 1i, sequence 2i, apply f to it, and I is in the length of the sequence. So n is here implicitly the length of the sequence. Yeah.
What operation is that trying to mimic in the transformer?
It's when you have multi-headed attention, after that you're summing up, or you have multiple, I don't know, like this sum up operation. Yeah. Which is actually pretty important, because then you can have these parallel working streams, and then you can join things, like you just pre-compute, and then like combine the results in some way. Yes?
With this language, we ignore layer norms.
We totally ignore layer norms. They have no. Oh, back to layer norms. Yeah. What I explained about layer norms, absolutely not true. Layer norms is a much simpler thing than what I explained. So what happens with layer norms is that this token processing function that takes a vector, computes the mean of the vector, subtract the mean, and computes the standard deviation of the elements of the vector, divides by that, so that after this normalization, the vector's variance is 1 and the mean is 0. This is it. And this is applied component-wise, oftentimes after MLP layers. Okay? And people differentiate through this, and sometimes the mean is not subtracted. You just want to somehow keep the statistics of whatever is being computed under control.
So is that component-wise, as in it's applied independently
To each position,
and
right?
Okay. So there is no cross position.
No. Yeah, there's no cross-position normalization at all. Yeah. So it's just very simple, like maybe the MLP is like, I don't know, doing something, going wide, and then let's just map it back. It's really mapping the surface of the unit ball, right? All the vectors. Yeah.
What scenarios really fit in when aggregation function is max or min?
So they are arguing that the max and the mean is kind of what you would get with some kind of attentions, not the softmax attention, but other attentions that people consider. People consider max attention per se. And so it's like, yeah, could be useful. Yeah.
Isn't it also just like when the softmax really centered on something, so it actually looks like, I thought this was just like the softmax
All this
if-
doesn't, all this wouldn't matter if the softmax returned a Dirac. Just 1-1. Like all aggregations would do the same, right?
Mhm. Yeah, I guess they call that usually, well, they call it hard attention, but like,
And that would be called hard attention, yes. So if you had hard attention, then okay, all of these collapse. And then sometimes people actually do this, they change the nonlinearity, or they omit the nonlinearity, or they change it to max, or smoothen max, or there are many different variations.
So in this example, we are taking all these things to be integers, but in general, they are like in the workspace, right? They're vectors.
That's
So
right.
what is max and min?
So this, like this language, in its effort to simplifying things, completely ignores the vector space structure and the complications that are coming from that. I think that the attitude is that, well, somehow the attention, like the transformer will deal with that. But somehow, the int 8 is like, okay, so that if your token space is already very small, then that's kind of like just saying that the workspace remains very small. One of the reasons that they introduced this int 8 restriction, so first, like these guys didn't do the int 8, it was arbitrary integers with Python allowing any, any size integers. But they want a learnable thing. And so for that, if your token space is really small, then you can learn any function. There you are losing something. You are losing interesting structure. But okay, like you gain some simplicity. It's okay, fair. Yeah.
So with this language, we need length, but in like the abstract.
We can't really use the lengths, or can we? I mean, so with this language, the length is never given to you.
Oh, okay.
All these functions, so you can only call these functions or sequences. This is all that you can do. And you compute new sequences and you can store them, and then finally you return one sequence. But there are only these 3 functions that you can call. There is nothing else that you can do. So for this, with this version, and so this is not the L version, and the reason for that is because here the attention is acausal. Or global. So if you wanted to calculate the length of a sequence, you could. Oh, there is one more function I forgot. We have position encoding. So we have indices. Function. So that just returns the numbers from 0 to n minus 1 as an array. Okay.
Could you repeat again, what function are we trying to learn?
We're not learning anything. We're trying to think like a transformer. We are modeling what the transformers can compute. Because we want to think about what can we even compute, and how will you compute something. And so for that, we are creating this language so we can abstract away some details and then experiment with what we can compute. Yeah.
You said earlier that the int 8 violates the vector space assumption. That's because you lose commutivity and stuff? And is that important?
No, it loses all the structure of a vector space, right? So all the complications that come, like the vector space maybe is an advantage or disadvantage, we don't know. What does the transformer do inside with the vector space? We don't really know. This is not even trying to model that. It's not forcing you to represent things with vectors and then do vector operations. Like in an actual transformers, when you implement things, you only have matrix vector multiplications, all these simple things, That's what you need to do. So here we abstracted that away. That's what I'm saying. It's like a different level of abstraction.
So then when you talk about transformers, you're talking about them as mathematical functions, and this is about real algorithmic implementations of them? Is that
Well,
what's
I mean,
happening?
it's if you look at transformers very generally, then this is a specific subcase of transformers. Transformers, the way it's practiced in deep learning, that's a different but very close related subset of transformers. So the way I define transformers, it was very general. It encompasses this and the real ones. Okay. And it's, yeah. First part.
Just about the vector space thing again. I think I guess to talk about it, there's like a compiler for this.
Yeah.
And you might ask like, how does it compile it into vectors? And the way like it'll do that, it'll map like the corresponding ints to just like one index of the vector. So it basically just maps it to like one.
Unit vectors. Like you can represent all the integers. Like you have as many dimensions as the numbers that you need to represent. Everything is orthogonal. You kind of lookup tables can be represented that way, right?
Yeah.
That's how it is done. So it's like, is this less general? But it's different because it's not even talking about, like there are interesting questions like how many dimensions you need to do some kind of processing with your vector space. You can't really address that. It's not in the workbook. But that's still an interesting question. But this allows you to think about more abstractly of like, what sequence processing operations can I do with a transformer? And we are going to see that in a second. Yes? It's similar. Okay. All right. Okay. Is this clear enough? So we have toke map, seq map, QV, and indices, and we can have simple functions that, like two types of functions, well, three. These are unary functions taking int8s, returning int8s. These are binary functions doing the same with two arguments, just returning one argument, and predicates functions, they take two arguments, int8s, and return true or false. That's it.
But you have an example of the little v?
We'll have a lot of examples now.
I mean, what is v doing?
It depends on what you want to do with the transformer. Okay, so let's get into it. Okay, so first, the job is using these functions, write a little program with pseudocode that takes a sequence, and that code is going to take, I don't know, two arguments as well, two integers, and every occurrence of the first integer or int8 is replaced with the other integer. Okay, so the synopsis for the function is that it's a replace function. It takes a sequence, and then there is a value that comes in, value that comes out, and this should do the following. It goes like, it should do this operation, return v out I if sequence I is v out, just this, is equal to v in. So these are integers. This is a sequence for e in n, where n is the length of the sequence. Kind of my pseudocode for what this function should be doing, but I can't write this because I need to implement this by calling toke map, seq map, kqv, and indices. I can't do anything else. I can't write this. I don't have for loops. I don't have branching. So we have these primitives. We have to use the primitives to implement what we want. This is what it means for a transformer to do this thing. So if you wanted to train a transformer that changes every occurrence of some character with some other character, the internal processing that it would need to do in some form or another would be somehow described with operations like this. Like, what does the attention block do? What does, right? Like, okay. Yeah.
Okay, last question. I'm kind of confused with sequence map because it's pairwise.
Yeah.
But when we think like transformers, they aren't really pairwise.
They're right, because we were talking about that there could be parallel threads of computation
Okay.
in a layer, like when I was kind of drawing, that sequence comes in, and then you do something, but you do something of the same kind multiple times, and then you join these things. So this joining operation, joining multiple things, and here we are abstracting it away to just joining two things, but if you can join two things, you can join any number of things, so there is no generality lost.
So are these functions kind of forming like a basis for the functions that the transformer can?
That's
yeah.
right.
Okay.
Yeah, exactly. Everything that the transformer can do is sort of like, is written in terms of these functions. Okay, so everyone think about the problem.
So what should that return for sequence where it's not equal to boolean? Should it return the original element?
Oh, yeah, okay, sorry. As it returns the original one. Sequence. So only the occurrences. Yeah, I didn't finish in my temporary confusion. So if there is a match, we are returning the new character. If there is a match with the input character, then we are returning the output character. In the other cases, we're just returning whatever we had at that position. So what does the transformer needs to compute to do all of these things?
Compute whether there's a match.
Okay. I recommend that everyone takes 5 minutes to think about this. Maybe discuss with a partner next to you.
I think this one's only sufficient to use KQV. I think KQV would be enough. I think. This function KQV? Because what if your predicate or something? Like if you're basically testing in the sequence if what's the word? Shouldn't KQV take a sequence? Anyways, you're basically taking a sequence and testing if it's in, and then you're replacing it with not, right? So that could be your definition for your either your predicate function or your aggregate function. Like you kind of like
You're trying to get a function that replaces.
trying to construct a place out of token map, sequence map, and KQV. Oh, you should just use token map. Yeah, you should just use token map.
Doesn't token map just get the length? That's all we do.
Doesn't return the function applied on each element of the sequence for I in range of the length sequence.
I'm kind of confused with that. Is the f kind of free that we can use, or we can define f in the token map?
I think token map takes the function f.
Wait, in the function.
Oh, but you can't make the. Can you make the function? Can you just put it in the function f that spits out?
Yeah, I'm not sure.
Other question. The function f we're only going to any operation functions, right?
I don't know.
There are any functions into H,
Just
into
implementing
int.
that.
I would assume so.
That function.
Wait,
Yep,
I just
maybe it's not too hard.
I think you do V out times just the binary indicator.
We are
So the function f in token map, can that be any function? So could we, I think I have an, okay. You perform it all, and you test. I think if you do,
implement that function with these basic.
like if you have sequence I and bin as binary numbers, then you want to do an AND. You want to do sequence in I and V in, and you perform an all. You want it all to be true, and then you multiply this by V out, and then this would be your F, and then you could do token map with sequence of F.
How do we have that operation?
You said you can use any function. I don't know.
Look at the operation.
Any function F in your token map. I don't know. It's like a map that takes think token map is a map that goes from the space of like I don't know int 8 to the power of n cross product with the space of all int 8 to the power of int 8. So it can take in and then it outputs an int 8 to the power of n number. I think I have an idea. Yeah, and then you could do this also. So you check if x is equal to bin, and if it is, then you multiply by b out. And if it's not, it's 0. Or no, it should be. I think you can just write that function, can't you? You can just write fx equals v out if x equals v in x else. Can't you do this?
Yes. But shouldn't you go characterize?
Oh, but you need v in and v out. Yeah, you do this character-wise. And then you do token map with sequence and f. Huh?
Like your app should be like KQD.
Oh, you mean because it has one takes
I know.
Yes.
So we define it.
But the thing is, you need f to take in b in and b out. B in and b out is a low-key variable.
App is KQD, but it takes the form of KQD. They should define like token.
Do you have an idea?
Yeah, actually, you can just use token map and sequence map.
Right.
First you
We have it? Someone wants to explain? Huh?
maybe I'm not sure, but we can just use token map and sequence map.
You need
First,
sequence map too?
maybe not. I don't know. We'll see.
Okay.
For token map, I think first we can see each index is whether equal to v in or not, and then if it was
Not index.
for
It's I.
for every
Index.
seq I mean
I see.
for every index of the sequence we can check that whether
At
it
that
is
position?
yeah.
The sequence equals vi.
If the sequence is equal to vi or not, and if it was, we can just replace it with 0.
Why
Yeah.
not vo?
We can
Let's do that.
let's
And if not?
and if not, we can keep it as what it was.
Right. So that's our function f.
Yeah.
So we just define function
It's
f.
basically this, right?
It was simpler than that.
Like this is what you basically. And you do token map sequence and that.
Yeah.
Exactly what's written here.
Yeah, but I mean, you can just design your
X
something
is
like that.
v in. Okay.
Yeah.
return
Oh, and like
v
another
in
like a
if x, no, v out,
Yeah, yeah.
Well, this is, I guess this is.
if x is v in, as return x.
yeah.
This is your function f. This is the MLP. The MLP is just like remembering this v in and v out, and then if it sees something, then if it checks whether it's v in, and if it's v in, it replaces it with v out, and otherwise it doesn't do anything to it. And then you just call a seek map on your sequence with this function. Okay, let's call it f something. So that not everything is just called f.
You mean token
Uh,
map?
Top map. Yeah, I keep forgetting that they call it top map. Yeah.
And then I think front X would need to also take in V in and V out as parameters.
Yeah, I mean, like,
And then-
yeah, well, MLP kind of suck. Yeah, this is true. Yeah, because otherwise the replace function is not general enough. So that was like maybe V in and V out are globals. So yeah. Like, okay. So that didn't require attention.
Yeah.
That was cool.
Yeah.
Like MLP stuff, it does this, right? Like it looks at the input and then like if it sees this, then it does this, right? And like it can do these arbitrary things. Okay.
Well, you
Something-
can also use attention to do that.
Huh?
You can also use attention.
Sure you can. And maybe when you're training the transformer, you'll use attention to do this. Who knows? But
Wait, but does this actually work if it doesn't take in V and V out? Because I thought it only takes in like one. Like V in is like, let's say a token, and V out is like a token, and then elements of the sequence are tokens, and then F can only be applied token-wise.
yeah.
And so, I mean, if you treat it as global, sure, but that's. not
Yeah,
actually
you
how
treat it
it's
as a global.
programmed.
Yeah. It like okay, so the transformer is fixed. Whatever is in it there,
Mhm.
it's like, okay, so this was like an ill-advised thing to do, that I take this as a parameter. Like transformers are not parameterized by extra things. Like you would need to change the architecture for that to happen. If you wish, you could try to do that.
No, but like, it would be like the input is a sequence that has the last two characters as V and V out.
Yeah,
And you have
that
to
would
do
be a
this.
different thing. So we can try to do that next, right?
Yeah, that would be
So
right.
now in the prompt, you have V in and V out. After that, you have a sequence, and you have to replace every occurrence of V in with V out. You go.
Oh,
All right. So the
Use
transformer
sequence map.
has to do. Oh, but okay. How do we do this? Okay, so we can do this in two different ways, or we can try to do it. So let me be very specific, right? Like, what is it I'm asking you to do? So one thing that I can ask you to do is this modified replace. This V in and V out in the argument, it's like not a transformer thing. For the transformer, if you want to ask it to be flexible to do things, you put that into the input, into the sequence. So here is the new replace function. So for every position that's in, okay, so the indexing starts at 0. So at index 0, we're gonna have V in, and index 1, we have V out. So let me correct this to sequence 0, and let me correct this to sequence 1, and here, okay, so we have to have two cases, but yeah, I guess it doesn't matter. For every position we do this, including the first two positions which are special. So in place, we are replacing every occurrence of the first integer with the second integer of the sequence, and we want to have a transformer to do this. Can we have this? Is this possible to do? How? Yeah.
Wait, what was the question?
Okay,
We
so
can make
I
this.
asked you to implement the sequence function for a global V in and V out, and we did that. Now I ask you to implement this other replace function, whose specification is fully on the board. You still have to do it with TOCMAP, SIGMAP, KQV, indices.
I know, if you sequence map,
Okay.
and you put in 2 copies of
How
this
do we do
one
this?
into F.
Think like the transform.
Yeah.
I guess the other thing to note is like we can define variables in the program that are like
Yeah.
the outputs of things and then
Yeah.
reuse them as inputs later on.
That's right. Because the transformers can do multiple parallel things, they compute. And so everything that you define though has to be returned by one of these functions.
And the functions can only return integers.
And they only return sequences of integers.
But like the F functions can only.
The F functions can only return from the int 8 to int 8. That's it.
So they can't even be like pairs of integers or something.
They cannot return pairs of integers. They can't do that. Like we have this 1, 2, 3 types of functions that you can use. That's it. But those functions are arbitrary. Okay.
One more question.
Yeah.
In the VI and the KQV function, we return VJ,
Yeah.
else we return 0.
No. You like just for the positions
Yeah.
that it was true,
We return.
you return that thing.
What if
And then
it's-
otherwise, like maybe it's empty.
Oh,
I don't know what the aggregation is doing if it's
I
empty.
think you might have to use attention.
Try not to use it.
I know.
Try not to use it. Maybe it returns
That's
error,
why
but
I
I don't know how. So if you look at the actual Python implementation, they will make some choices there, and like, yeah, you better avoid that.
Well, max should return minus 128 and min should return plus 127. Like max should return minus 128 and min should
Yeah.
return minus plus 127. Mean should not. Yeah, mean is.
Me should not be called on such things.
And mean should return infinity. But that's not anyway.
Right.
No, it should take the mean of the values.
No,
Yeah, the mean of an empty array doesn't exist.
So
So.
somehow the empty array is 0 and divided by 0.
Well, hopefully we will not need the special case when the array is empty.
No, it's not that about the reason, like, about the positions where AIJ is false.
You just ignore those anyways.
Anyway, okay.
And
Yeah.
if the idea is always false, then you're in trouble.
No, that's not me.
But you would be in trouble.
We could construct our own sequences, right?
Yeah.
Nice.
So, AIJ, somehow needs to depend. Oh, yeah. Yeah, so you need one function. I guess implicitly here assuming that in this lesson 128, because I think this is function returns a byte, so it has to exactly.
Yeah. I guess in this is a different data type. Somehow, somehow you can, yeah, let's not get into that. It's, yeah.
Because otherwise you just use sequence true as a resource already. But that would be too out of what we are supposed to write.
Yeah.
Sequence 2 will be at sequence 0, and actually like we just compare sequence 1 of I get a boolean, the result of this hash will be called as F1. We get a boolean array wherever like s of I equal to sequence of 0 will get true. Then rest everything is false. Now this refers to another F2, which takes this original sequence and this 2 goes to wherever it's true, we will replace it by sequence of
Because we don't have V in and V out. We have to extract V in and V out from the first two indices.
So you use this here to
Just wait, I almost have this. This is so sick. Find f x y equals to 1. Oh, I got it. I think I have it.
maybe you could use other token map. Use token map and like an empty sequence and like use another like true. Let's call it another one true function. Yeah.
I guess instead of converting it to true or false, so instead of converting it to true or false, I just use the values here itself.
Maybe you could use token map now.
Okay, I think we should discuss the solution. Anyone has any solutions? Yeah?
I have like a rough solution. I'm almost there,
Yeah.
basically.
Yeah. We're starting.
I think I'm going about it like a long way, but
Yeah.
my idea is like we want to construct frep with a v in and a v out parameter, but we don't have that available.
Okay.
So we want to construct a function that'll pull out v in and sort of do like a mask is what I'm thinking.
Okay.
And then multiply the mask, and then another function that does it with v out and multiplies by the mask.
Okay.
Then you do like an OR process basically,
Okay.
and then you do a sequence map on the string with all v-ins with your original and
Okay.
with the one of the maps and so on, and then you do like a token map basically with that frep. That's like the idea. And then,
Something like that.
yeah.
Did you follow that?
Yeah. Did this make sense?
I don't know. Maybe you were not loud enough. For the both, whether in the back, people, did you hear it? It's kind of sounded complicated, but it's just masking and processing. If we had, okay, so at the very high level, there are two things that you have to do. So you have an input that comes in, and the first position has V in, second position has V out, and the third position index 2 has something, and then all of these things up to the end. And first you want to broadcast V in to all the positions, because you can do this sequence by sequence processing. So you somehow want to propagate V in to all the positions so that they're available for comparison. That was very conveniently done here with this global function, but we don't have that now because v-in was part of the input. So we have to propagate v-in throughout. How can we write something that propagates v-in throughout? Like field array of lengths, whatever the sequence was, with v-in. We should be able to do that in some way. Which operation is going to do that?
It's just token map
Token
with a
map.
fixed function that gives the v in, no? The first
But
sequence.
v-in is part of the input. It just, yeah.
So I was saying you use sequence map and you
Right.
construct a sequence that's
How
made.
do I construct the sequence that has v-in everywhere?
Yeah.
Oh, you're not. That's illegal. Yeah,
I
that makes sense. Yeah,
I
yeah.
can only
that's-
call those functions.
Yeah, that's the same word.
Yeah.
So you want to use an intention layer.
Yeah.
You just use the KQV with K and Q equal to the sequence.
Okay.
So then the attention mask will be ones everywhere.
Okay.
Or wait, that's not true.
Yeah.
Or you can make the attention mask ones everywhere. I forget how you do it. And then you just aggregate with the min, and then you get the.
Oh, why? The mean aggregation takes a
Oh, wait,
value,
no, it was
so.
fine. You get the identity this way,
Huh?
and then you aggregate with the. I don't know if you do the min. I guess it doesn't matter what. you
It
do.
doesn't give you the identity if you have repeated elements. It gives you this pattern
Oh, then you
matrix.
do the min. I think the min will work fine there.
Almost. Maybe in the back.
Maybe use indices to get all the indices, then you use the token map to get to attend to or just a binary operation on the first index. Then you use KQV.
So what does token map does with the indices array?
It just says that it's a zero index or not, zeroth index or not, basically Boolean operation.
It should return an integer.
Yes.
F?
Zero or one.
0 or 1?
Yeah, zero if the index is not zero, and one if the index is zero.
Okay, so we can construct this thing.
Yeah. And then that should be the key, and the query should be.
Oh, that's smart.
Maybe there is a simpler way, but yeah, something like that.
Yeah.
So this attention matrix. So there are the keys and the values, and there are the queries. And for each of the query, if I fill out an attention matrix so that actually I'm picking out the right values, I'll be done. The right value should be whatever is in the zeroth position, right? So what should the attention matrix be? I should attend to the zeroth position. So somehow I want to construct an attention matrix that looks like this, right? Once I have done this, I put in the values, just the original sequence, okay? If I do that, if I have this attention matrix, in the output, what am I going to see? Is the zeroth element of the sequence, that's V in.
Yeah.
So in the output, we're gonna have sequence 0, sequence 0. Okay. So that will do this broadcasting. What remains is, how do I get the attention matrix of this form? Series of ways. You create with the indices, you create a special predicate function that says that, well, I don't care about like.
The predicate is one of the two main parts of the sentence, the other being the subject, which the predicate modifies.
Thank you, Siri.
This is
Take it easy.
Intelligence interferes. Okay, so you could have maybe this is 0, 1, to n minus 1. This is 0, 1 to n minus 1. And your predicate takes, I don't know, this was query. So the predicate's first argument is the query, second argument is the key. And so it says if the key is 0, I return true, otherwise I return false. That's your predicate. Now you created a matrix. You do set the value to sequence, and then you were broadcasting everything. Beautiful. So we can broadcast V in everywhere. We can also broadcast V out everywhere. Same idea. Kind of hard work though. It's like a Fourier transformer has to work pretty hard to make all these things happen. Okay. So once you have this, if you had a ternary sequence map, you have S1, S2, S3, and you can apply a function that takes 3 arguments, you would be done. Because what that function would do is that position by position, it would take a look at each of the arguments, and it would be like, oh, if the first and second arguments match, then I would put the third, otherwise I would put the first argument. We don't have ternary functions. We can do a workaround. So we do 2 binary things. We have binary functions. So we can do a binary thing that looks at here and then creates this mask that you were talking about. That kind of just masks the positions of V-ins with a special character, which should not be part of the input. So there we're hacking a little bit, like there is this, I don't know, minus 127. It's not used everywhere else in the input. And so that first function, what it's going to do is that it looks at the 2 sequences and it merges them in such a way. It looks at the first sequence. If the first sequence element matches the second, then it returns minus 127. Unfortunately, it cannot return this because it doesn't, but it can do this special characters thing. Minus 127, it returns that. And otherwise, it returns whatever is so in the first position, first argument. Okay? So from this, we created this masked thing where every occurrence in the input string of V in was replaced with this special character minus 127. So now we can go through that and the V out, again, binary processing, and create this other function that looks at the input, and if it sees minus 127, then it returns the second argument, and otherwise it returns the first argument. That's it.
I don't even think you need a minus 127 value, because you can just use Vn. Like if you, every time you see it matches, oh, it needs to be a non.
Well, it doesn't, the second function doesn't know what V in. That's the problem we are trying to circumvent by introducing this special value. That we have binary things and like you actually have to implement ternary thing. How do you?
But can be.
Yeah, maybe, but yeah, we have a different solution where we use KQV as a ternary operation, and then you know we take like a special value.
So you could do that.
Yeah, so we just have 3 invocations of KQV, and
yeah. So you can avoid this special processing. Anyways, so we already see that attention comes in very early, even if you have to do really silly things.
Attention is a function of the token, right? Token plus position. It doesn't have to be just a position, right? Am I right?
So here, attention was the function of whatever sequences you give it. And we couldn't possibly combine positions and values in like the same key, for example, doesn't have both elements. This language doesn't know that. It's kind of a limitation compared to position encoding if you wish. But yeah, you know, can transformers really do the position encoding? So okay, so the learnable part of this language, this L modification, what it also does is that it restricts so it introduces an index type. So the index types can be used with index types, but you can only compare them for equality, less than, greater than, and you can only increment them by 1 or decrement them by 1. These are the operations that you can do on the index types. This wants to model that transformers will not be able to deal with arbitrary position arithmetics. Okay, so the next text, but we don't have a lot of time, would be to reverse a string in place. And you can imagine how to do that. You would need actually index arithmetics for that. So you could try this. You create the indices, and then you create the lengths. For that, you need to have a global attention. If you want to broadcast the mass, the lengths of the strings, it only appears in the last position. To have it appear in the first position, if you want this in place thing, you have to have global attention. If you have acausal attention, which is part of the restricted language, you won't be able to do that. But okay, let's say you have global attention, then you can broadcast the lengths to the first position and everywhere. So you can fill an array with n-1, and then you can subtract the 2 from each other. So that's arbitrary index arithmetics. So okay, like maybe you can do that. That would be a big assumption, and might not really work very well for transformers when they are learned. But if you do that, then you can create this other array. So you have this n-1, m-1, you broadcasted it everywhere. So you subtract from the second the first, so that's just a seek map. So then you get m-1, m-2, and 0. And then you can just use this to pick up the reverse elements. Right? How? Well, you can create this attention matrix that has the A diagonal equal to 3. By comparing indices to the reverse of the indices which we just created. That creates this A diagonal matrix, and that attention matrix allows you to pick the values in the reverse order. You reverse the string in place. This required global attention 2 places, this broadcasting of n, and also this reversing at the very end. It was not an acausal attention. If you have acausal attention, how do you convince yourself that in place reverser of sequences is not possible? Because it's not possible.
But if you have causality.
Oh, I'm so sorry. Yes, if you have causal attention. That made no sense. Yeah. If you have causal attention, this was using acausal attention, global attention. But if you only have the causal attention, then this in-place reverser is not going to be possible. How do we see that? Yeah?
You won't be able to know what's in the last place when you are in the first place.
Yeah, you need, like, if you have a causal transformer, it's auto-regressively calculating everything so from an input, it constructs an output in a seemingly complex way. But if it was auto-regressive, then if you look at some output position, this can only depend on whatever happened before.
But can we have multi-layers and then, for example, shifting the I don't know, the indexes that we have at
This
the end?
restriction doesn't go away.
But you have sequence map. Can you use that?
Huh?
You also
The
have
sequence map, the sequence map is adhering to the same pattern. It doesn't allow you to peek forward. Your output cannot depend on what comes later, ever. So with causal attention, You can only implement functions that take this form. And in place string reversal is not like that. It's a function where to know what to put here, you have to look here. Can't do that. You can only look here.
So we only have triangular attention matrix, right?
That's right. Yeah. That would be the A causal. So J is less than equal to I. That's the causal attention. Okay. What's the way out? That's like a big deal. This autoregressive processing, chain of thought, or whatnot. So we can still reverse strings with transformers. We see it all the time. How do they do it? Well, we don't want to do this in place. It's called an autoregressive mode of the transformer, which we talked about before. That you do all this calculation, you calculate the new sequence, but you only take whatever appears in the last element and you paste it to the end. And now you have a sequence which increased in length. And then you can process that. And then you process it, and process it, and so on and so forth. With this, can you reverse the string? To some degree, if I put a special marker here to denote the end of the string, I can definitely do it, right? Then you can write this little function that looks at, like something was produced already, it seeks out the position of the special character, and then it does some arithmetics on where it has to look. So this distance has to go back and then do one more, and then that's what it needs to copy here. And that you can do with causal attention. Okay, we don't have time for that, but maybe let that be a homework to think about how you would do this. And then I tell you, maybe on Slack, I will just post the address to, and you shouldn't pick there, maybe the solution is going to be there. There's a GitHub library where you find the implementation of TalkMap, SIGMap, KQV indices that implements this special little library. And then it's so fun to play around with this. Yeah. And then you should just try to implement this autoregressive way of doing things, and maybe other things if you have some other ideas. Okay.
Why should we be so restricted? Like, why should we say?
Which restriction is that you don't like?
I mean, just do these kinds of operations that can be easily done with using just normal computation. So why can we say we consider transformer plus these operations that say the language model can actually call subroutines that the language model can actually directly call them instead of doing awkward things to implement them.
Yeah.
Why we are not interested in those in that framework? Instead, we had to say we just restricted it to these transformers and investigate what they.
Yeah, this is to build our empathy for transformers. Yeah, so that you feel what they have to do. It's like, poor transformer needs to reverse the string, it has to do all these operations. It's like really horrible.
But maybe
And then yell at it.
Like if I say reverse this sentence, it understands what I mean and it can call.
Why? Like it just does simple operations like this. It has to go through all these hoops. So this is indeed, it helps us to really feel or understand what a transformer has to do in order to do really simple operations. That's the point of the exercise. And later we're gonna talk about, like more mathematically, rigorously of like, what are the functions that you can represent with transformers and what are the things you can't. But I think that this exercise teaches us a lot about, the difficulty that the transformer is going to, like they need to learn these things on the top from data. That's like not even talking about, like that's even harder, right? Like they have to solve these induction tasks. Okay, and we didn't talk yet about like, okay, the title of the course has reasoning in it. So what do I mean by that? I don't want to get into philosophical debates about what reasoning is. To me, in this course, this would mean that you can teach whatever neural architecture or whatever machine you want to use, system, to perform calculations in a reliable fashion for you, which have well-defined outputs, right? So if I ask one of you to check a proof for its correctness, we think that the result of that is well-defined. You can do it, right? Like there are some steps that you have to follow. Is this true? Is this not true? Like, are there some gaps? So the result is verified. If I give you a word problem, if I am careful enough, it's well defined. There is a unique solution to that, and the solution should come out at the end. So now people are trying to teach these transformers to do all of these computations for us, the computational tasks with well-defined solutions. And sometimes they get them right, sometimes they don't. We want them to get the answers right all the time. These exercises help us to see what it would mean to have that. Not talking about the neural implementation detail, this is like conceptual level, but it already gives you an insight of the hurdles that a learning algorithm has to overcome to be able to implement some really simple functionality. So in a way, this also wants to take out the magic of all of this, right? Like we need to understand what these things can do, what they can't do, and we're going to talk a lot about the learning stuff, whether from data it is even possible to learn to reverse a string, and how much data are you gonna need? Will that ever work? That's much simpler than from data learn natural language and along the way learn how to think like a human, just like that. So the simpler tasks, we want to understand those, and through understanding the hurdles faced when you try to convince such a neural thing to perform the computation you want them to do, understand what it means to for these bigger models to be able to do certain things, or why they are not able to do the things we want them to do. And then maybe we're gonna have some ideas about how to fix that. Yeah.
So do we know what is the span of these functions? I mean, is it a study that what functions that these functions can implement?
In a way, Vlad is going to talk about some very close related questions. So the RASP language, what it can represent or not, it's a little bit ill-defined, this language. So it's like, it kind of bleeds left and right. Because of int8 and like what exactly it means that like the index arithmetics is restricted and whatnot. So people didn't really study this seriously, and it probably would be just a waste of time to study it. I think that this is very good for this level of building a conceptual understanding, but it will not really have that much to understand what transformers will be able to learn. This definitely gives you a feeling of like what they won't be able to do. Right? Like it's reversing the string in place. If you have causal attention, clearly it's not going to be able to do that, and you don't need to have any lengthy proof. But yeah, it stops at some high level.
Is there any reason for why you chose replace and reverse? Like, do they form some sort of basis of other functions?
Yeah. So you could think about like elementary operations, such that if you could do all those elementary operations, you can do a lot more, especially with autoregressive processing, and then some of this is also going to be talked about. So one of the thinkings of like how to make transformers universal and be able to do a lot of different computations is that you break the computation into elementary parts. If it can do all the elementary parts, then like why it won't be able to do the complex calculation? It should be able to do that. So yeah, there is that thinking. But here there is no claim for the universality of reverse or broadcast or whatever. But maybe some people in computer science actually study like some universality questions related to this, but yeah, there are no claims about that. These are somewhat arbitrary examples. Nevertheless, people are experimenting also with these things in practice. And so there is, like these papers are empirical papers. People are trying to teach transformers different operations. They make observations about what works, what doesn't work. And in a way, this language with the L restriction is geared towards what's learnable with transformers. So this is RASP-L hypothesis that says that, well, on the one hand, if a transformer can learn some sequence processing operation, then it will have a short RASP-L program. On the other hand, if it has a short RASP-L program, then the transformer will learn it. I don't believe that this is literally true, but it's been correlated with some empirical evidence. It's not an outrageously bad hypothesis. I certainly feel that if the RASP description of the task is really big, like lots of lines of code, by the way, notice that all this code is just straight line code. So that was a big name of the class. It's just no if, no loop, no nothing. It's just like do this, do that, do that, do that, do that, do that, do that, bam, and because it's a transformer that has so many layers and does so much computation. Where was I? Yeah, so certainly I feel that if we try really hard to write a short program in RASP-L for some task, and this program happens to have a lot of lines, then maybe this will be hard to learn. Because then I just like there is tremendous complexity in this task as far as a transformer is concerned. Yeah. All right. Okay. So let's stop here. We're a little bit over time. For people trying to find